Good day, everyone. Today we shall be considering the quantum number. By the way, this is Gifted Brain, aka Saizu, first in Africa, sixth in the world. You see, in quantum mechanics, we use the quantum number to describe the distribution of electron in an atom. Yes. And there are four sets of this quantum number. The first being the principal quantum number. The second is the azimuthal, which can also be called subsidiary quantum number, or you say angular quantum number. And the third is the magnetic quantum number, and the last is the spin quantum number. Let's take the first quantum number. That is the principal quantum number. And this describes the energy level an electron occupy, or in other words, instead of saying energy level, you can say the shell an electron occupy. And before now, we've been able to say that electron exists in levels. The lowest energy level an electron can be is the K shell. The next is the L shell. After the L, we have the M shell. As we keep moving to N shell, that's the higher the level the electron occupies. We have K, L, M, N, O, P, on and on. And now, when I say N, which is what the principal quantum number is represented with, when I say N equals 1, I'm talking about the K shell. If I say N equals 2, I'm talking about the L shell. If I say N equals 3, I'm talking about the M shell. On and on. Okay, now we move to the next quantum number, which is the azimuthal quantum number. You know, before now, we've also been able to establish the fact that we don't know where an electron occupies in an atom. We cannot say this is where an electron actually is. Yes, the uncertainty principle buttresses this fact. Now, what we can actually say is that we can predict, well, a region of space in an atom where electron most probably should be. And then this region of space are called the subshell. This azimuthal quantum number, this second quantum number, describes this region of space. And then it is represented by letter L. If I say L equals 0, I'm talking about the S subshell. Or in other words, you say sub-level. If I say L equals 1, I'm talking about the P sub-level or subshell. If I say L equals 2, I'm talking about the D sub-level. And its number depends on the principal quantum number. Yes, it takes one less than the principal quantum number. For instance, now, if the N value is equals to 2, I'm talking about the L shell now. The possible shapes, the possible region of space we can have is the 0 and then the 1. 0 for the S and 1 for the P. Now, for instance, if I say N equals 4, for instance, the possible space the electrons could be occupying available to us will be L equals 0, L equals 1, L equals 2, L equals 3. So it takes one less than the principal quantum number. This region of space has their own shape, the way they look like. The first, which is the S, is actually spherical. The S is spherical, looking somewhat like this. And then we have the P. The P has a dumbbell shape, looks somewhat like this. The region of space where these electrons, which are in the P, occupy, looks like this. And we have 3 of this P. This P sublevel has 3 different P orbitals, the Px, Py, and then the Pz. We also have the D sublevel. The D sublevel looks like you can see here. And we have 5 different orbitals that make up the D sublevel. And then we have the F. Yes, the F has a complex shape. We cannot really describe what it is. Like I say, this is dumbbell, this is double dumbbell. The shape looks really complex. Then that's that about the azimuthal quantum number, which describes the sublevel, the region of space the electron occupy. We move to the next quantum number, which is the magnetic quantum number. Yes, this describes the orbital the electron is occupying. When we talk about the P, we say we could have Px, we could have Py, we could have Pz. Now, when we talk about the magnetic, it tells us that this electron should be in the px, should it be in the px, should it be in the py, or should it be in the pz? Or it's telling us that if it's in the d, as we have 5 different p orbitals that make up the sub-level, should it be in the first d orbital, or the second, or the third, or the fourth, or the fifth? The f has 7. Should it be in the first, second, third, fourth, fifth, sixth, or seventh? So it describes the orbital within the sub-level this electron should occupy. That's what it describes, and it takes values of minus L through 0 to plus L. So that's what it takes. I would, in describing these quantum numbers, telling about the n equal 1 and 2, I will give details of how this m value, we see how this m value works. But when we say m, we're talking about the magnetic quantum number. And lastly, we talk about the spin quantum number. This really just refers to the spin of an electron and the orientation of its magnetic field produced by that spin. Yes, it takes number of plus half or minus half for each orbital. Now we shall be taking quantum number through n equals 4. Here I'll be buttressing the quantum number, each of the quantum number. The quantum number through n equals 4. Yeah. Okay, so let's look at something here now. If I say n equals 1, obviously I should be talking about the K shell. And now, what are the azimuthal quantum numbers you have, or what are the L value? The L value we have is L equals 0, because you remember that we said that L takes values of 0 to n minus 1. So it takes 0. That L equal to 0 stands for the S subshell or S sublevel. Subshell. That's what it stands for. S subshell. And then our magnetic takes value of minus L through 0 to plus L. So what we have here is just 0. 0, yes. 0. But unlike minus 0, 0 and plus 0, everything just means 0. And then, that talks about, 0 here talks about the x orbital. The x orbital. So in the x subshell, you have just only x orbital there. Now, you see this x we have here, I will call it the 1x. It is the one, actually 1x. 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 Okay. And then the spin is plus half and minus half. So we have plus half and minus half. Now, when we look at n equals 2, we'll be talking about the L shell. And then the azimuthal quantum number will be L equals 1. L equals 0 and then 1. L equal to 0 and 1. Now, if L is equal to 0, I'm talking about the S sublevel, X. If L equals to 1, I'm talking about the P sublevel, remember. Now, this X, I will call it 2X. And this P, I will call it 2P. Remember, this 2 you are seeing here is corresponding to the N value. And instead that the X you have here in this N equals to 2, this X is not the same as the X in when N is equal to 1. That one is 1x. But the X you have here is 2x. It belongs to another, this X sublevel belongs to another shell. So that's what we have. And then the magnetic quantum number will be 0 here, 0, which corresponds to X orbital. Now, for the L equal to 1, which is the P sub shell, we have the magnetic quantum number, our M values will be minus 1, 0, and then plus 1. That's what we're talking about. That it takes values of minus L through 0 to plus L. So, and that's why whenever we draw the P, we draw it with, when we use box representation for orbitals, we use 3 boxes inside of it. 1, 2, and then 1, 2, and 3. Yes, the first one actually is called px, second is called py, third is called pz. But this ps is corresponding to the m equal to -1. This py is corresponding to the m equal to 0. This pz is corresponding to m equal to +1. So these are the three boxes that came from these three m values. Now, another thing I want to say is that you can see that now in the p sub level, we actually have three different p orbitals. So that tells you what a sub level is. Sub level is not, maybe it simply just means orbitals of the same energy. Orbitals of the same energy. Yes, that's what a sub level means. So in the p sub level now, we have three different orbitals there. So that's what is there. And then our x value, which is the spin quantum number, our x value will be plus half minus half, while for the p it will be plus half minus half for each orbital. Yes, for each orbital, because there are three different orbitals now. So you will not just say plus half minus half. You say plus half minus half for each orbital, and then we look at n equals 3. N equals 3. For m equals 3, I should be talking about n equals 3. I'm talking about the m shell now. So our Zibunda quantum number will become L equals 0, 1, and then 2. And so you see here now, I will have L equal to 0 is x sub level, s sub level. L equal to 1 will be p sub level, and L equal to is the d sub level. But here it will be 2x, it will be 3x, sorry, 3x. Here will be 3p and then 3d. Talking about the shell they belong to. So these three here, these three values you are seeing here, just talking about the shell this x, p, and d belongs to. And obviously, the m value, which is the magnetic quantum number, will be 0 for the x. Then for the p, it will be -1, 0, and +1. For the d, it will be -2, because the L value is 2. So -2, -1, 0, +1, and +2. So you see that in the d sub level now, we have 5 different orbitals. That's why when we use the box representation for orbitals, when we draw the d always contains 5 boxes, as I'm going to show you now. Something like this. That's what the d looks like. Whenever you draw the d, when you're writing the electronic configuration, this is how it looks like. And they have their own dxy, dxz, dyz, on and on. So each of these orbitals have their own. And then when you talk about the spin quantum number for each of these orbitals now, you have for the x, we have plus half and then minus half. But when you get to the p or the d, you say plus half minus half for each orbital, for each orbital. Yes, don't mind my writing. For each orbital, the same goes for the d also. Plus half minus half, so for each orbital. Plus half minus half for each orbital. For plus half minus half for each orbital. So don't of just writing it. That's what it is. Now let's look at finally n equals 4. At this point in time, I would want you to take a pause and then try it on your own. It's very, very easy. When you try it, you see it will give you exactly what I would also get. So that's about that.